Hi everyone. So today I will explain about the analysis of statically indeterminate structure with using moment distribution methods. So in the previous videos you already learned about the slope deflection method. Okay, so this is moment distribution methods. So general principle and definitions is this is developed by the Hardy-Cross in 1930. And the moment distribution is a method of successive approximations that may be carried out to any desired degree of accuracy. And then, okay, the sign convention is the clockwise moment that act on the members are considered positive. Okay, and then the counterclockwise moments are negative. So here means, okay, if it is clockwise, so it is positive. If it is counterclockwise, okay, then it is negative. So the fixed end moment, okay, this is similar to the slope deflections methods. Okay, so at here I will not press so much at this one, but I will explain in the example when you have the fixed end moments. Okay, it is similar with the slope deflection methods. Okay, so the moment stiffness factor, you can see it here. Consider the beam in this figure, so which is pinned at one end and they fix at the other end. So applications of the moment cause the end of A to rotate to an angle. So okay, when this will cause an angle. Okay, and then by using the conjugate beam method, so you will get K M equal to 4 EI over L times theta A. So you will get K is 4 EI over L. Okay, so when you use this method, then you will get this. So K is the stiffness factor at A and can be defined as the amount of moment that M required to rotate at end of A, okay, of the beam theta A equal to 1 rad. Okay, 1 radius. 1 radian, sorry. Okay, so you will have to find it, okay, with using K equal to 4 EI over L. This is the stiffness factor. So distribution factor, we also have the distribution factor. Okay, so distribution factor basically is the K over total K. So if a moment is applied at a fixed connected joint, so the connecting member will each supply a portion of the resisting moment necessary to satisfy the moment equilibrium at the joint. So at a joint, okay, so each member will have to support a portion, okay, to make it in equilibrium. So that fractions of the total resisting moment supplied by the member is called the distribution factor. So we need to redistribute, okay, at each joint, okay, we will distribute according to the distribution factor dF. So the distribution factor of a member is equal to the stiffness factor of the member divided by the total stiffness factor. So K over total K. Okay, so now you just now the equation you will use it in the examples. Okay, so for examples, here, so this is an example. So the distribution factor, a member AB, this is a point A, the joint A. You have AB, AC, and AD. Okay, so this one is provided already. The value of KAB is equal to 4,000. KAC is 5,000. KAD is 1,000. So the total is 1,000, 4,000, 5,000. Total is 10,000. So how it being distributed to these three members is according to their stiffness. Okay, stiffness factor. So it distribute to the AB by 0.4. Okay, 4,000 divided by 10,000, and then this one is 0.5 for AC. Okay, for AC, and then for AD is 0.1. So it distribute to here is 0.4, here is 0.1, and here is 0.5 accordingly. Okay, you will see it's more clear when I show you the whole examples later. Distribution factor, okay, for this example, okay, if moment is 2,000 Newton meter as joint A, okay, at joint A here, okay, 2,000 Newton meter, the equilibrium moments exerted by the members are at the joint, okay, so MAC, just now you DC here is 0.1, 0.4, or 4, 0.5. 0.5 here. So when the moment applied on it, okay, it will distribute to these three parts. Okay, so where this one will take 10%, this one will take 40%, this one will take 50%. So 0.4 times 2000, you get 800 Newton meter. Okay, so here you will get 800 Newton meter, and at MAC you will get 1,800 at 1,000, and here you will get 200 Newton meter when a moment 2000 applied on it. Okay, so means this is the distribution factor, how you distribute to these members. Okay, so it's total K over total K. So member relative stiffness factor, okay, quite often a continuous beam or a frame will be made from the same materials. So the modulus E will be the same. Okay, normally the E will be the same because they are making from the same materials. So if this is the case, the common factor for E will be cancelled out. If let's say, okay, it is same and then you are using the moment distribution method without modified anything. So sometimes you can cancel out the 4E or you leave it there. It will be the same. Okay, when the distribution factor for a joint is determined. So also some of the example you will see they will directly use KR equal to I over L. They will cancel out the 4EI. The 4EI over L, they will cancel out the 4E. If you leave it there, it's also okay. Okay, it's okay you using this or either using this. Both, you will get the same answer. Okay, so let's look at this short note that I made for the moment distribution method. Okay, so this purpose is to find the moment at support and end moment by using the table method. Okay, you have three concepts here. So first is called carryover factor, which is a CF. Okay, and then you have distribution factor, DF, and then the fixed end moments, okay, which is similar to the slope deflection method. So these three are very crucial, and you make sure you get the correct one, or else you won't get the correct answer. So the first carryover factor, you can see that here the value is either 0 or 0.5 only. Okay, so you can see that when it is 0.5 means this is the roller or fixed end to the roller pin. You can see A to B, okay, you get 0.5 here. And roller in the middle or pin in the middle to the roller or pin end, you will get 0.5. Okay, from C, you can see that CF for the BA, B to A is 0.5, and CF to the B to C is CF to the B to C, okay, pin roller to the fixed end is 0.5. Okay, and then you can see that CF, CB, C to B, fixed and fixed end to the roller or pin in the middle, you will get 0. Okay, so 0 and 0.5, and then you can see that here another example, A to B is pin end to the roller, you get 0.5. Same with this case. Okay, and then this one, B to A is roller to pin to the roller to pin end. Okay, roller to pin in the middle, sorry. Okay, you get 0.5. And then roller to the roller, you get 0.5 also. Okay, here mentioned it here, you can see this. Okay, and then but then C to B, okay, is also 0.5 because it's the pin roller end to the pin roller. And then C to D, you will get 0. Okay, when it's to the free end side. Okay, this is cantilever at here. Okay, means that you have no joints here, so you will not distribute. Okay, carry over factor, carry it to this D. Okay, so it's 0 when you have a free end at here. Okay, so next we go to the distribution factor. Just now is CF, so now is DF. Okay, so the formula, as I explained in the theory before, you have K over total K. So the K value is using 4EI over L. Okay, so it's either fixed to roller or pin, you will get 4EI over L. Pin roller to fix, you get 4EI over L. Pin to pin, you will get 4EI over L. However, pin roller to the free end, you will get K equal to 0. Okay, so if you have free end, then you will not distribute to that free end. So the K will be 0. Okay, so for this example, you can see it here. Okay, from A to B is 4EI over L. From B to C is also 4EI over L. KAB and KBA the same. KBC and KCB the same. All are 4EI over L. So what you can to do is now is the distribution factor. After you determine all the K, you need to get the DF. Okay, so the DF here, you can see that this pin roller end, at point A, okay, is total KAB over KAB plus KAA. Here you have only KAB, but then you don't have anything at the left. So you will get 1, okay, and then because KAA is 0 at the pin or roller end here is 0, so is 4EI over 4EI over L plus over 4EI over L. Okay, so let me write here. Okay, so you can see that here is 4EI over L over 4EI over L. Okay, so that's why you plus 0. So that's why you get 1. Okay, so that's why you get this value 1. So let me clean this. Okay, so for the next, you can see this dBA is equal to KBA, okay, KBA over KBA plus KBC. Okay, so this one you will get 0, you will get 4EI over L, and then 4EI over L plus 4EI over L. Okay, so you need to get this. Okay, and then there's BC also the same, is KBC. Okay, is KBA plus KBC at the bottom. Okay, so it means that when you want to get the distribution factor, you need to find it, determine it according to each joint. What is the K you have at the stiffness factor? Okay, so let me reduce this. Okay, and then KCB. Okay, is from here to here. Okay, and here is KCB over KCB plus KCC, where KCC is, okay, infinity. So basically we assume it to be not 0. Okay, it's something unknown. Okay, so KCB is 4EI over L over 4EI over L plus unknown. So this one you will get 0. So remember, when you have a fixed end, the dF is 0. Okay, remember for this, is 0. Okay, when you are at the pin roller, here is 1. When you're at the fixed end, here is 0 for the dF. Now, so let's look at this example, okay, for the moment distribution method. So, okay, draw bending moment diagram and shear force diagram for the beam below. Okay, and then now this is a statically indeterminate beam. Okay, then you have a 80 kilonewton applied at the middle from A to B. Okay, and then this is I, and then this is 2I. Okay, so be careful with this if it is different. Okay, and then you have a uniform distributed load 65.5 kilonewton per meter from point B to C, and this is the distance of each. Okay, so okay, this is the calculations of it. So after you determine that it is statically indeterminate, then you will find the CF. Okay, so first is CF. So A to B is CF AB is 0.5, BA is 0.5, BC is 0.5. But then from fixed, okay, fixed end to roller, remember the fixed, it will be 0. And then the distribution factor DF, okay. So KAB, KBA, KBC, and KCB are all 4EI over L. But then when you put in, you remember this section is 2EI. So for the KBC and KCB, the stiffness will be 2I. So when you put in a value 4EI over L, okay, 4.5, 4EI over L, you put in this, you get 0.89 EI. And when you get this, okay, BA is also 0.89 EI. Then BC is 4E times 2L over L. L is 3.5. So it's 2.29 EI. And this one is also 2.29 EI. So when you want to calculate the distribution, after you get a K, then you get a distribution. Okay, distribution is the K at K, okay, over the total K at that support. Okay, at that point. So KAB is over KAB plus KAA, where KAA is equal to 0. So after you substitute into it, okay, this one is 0. So KAB over KAV plus 0, you will get 1. Okay, and then KBA. KBA is KBA, the FBA is KBA over KBA plus KBC. Okay, at here. So it's 0.89 EI over 0.89 EI plus 2.28 EI. So this is 0.28. And then EFBC is KBC over total K at point B. Okay, so after you put in the value, you calculate, you get 0.72 EI. Okay, so for checking, so total D, BA and BC must be 0. I must be 1. Okay, so means that when you have a load here, okay, at B, it distribute to here 0.28 and to here is 0.72. Total must be 1. Means that the moment distribute 0.28 to the left, 0.72 and 72 to the right. And then for KCB, okay, at KCD over KCD plus KCC. At the free end here, the KCC is unknown. Okay, so you assume this is equal to 0. At fixed support, there is no distribution to the left and right, no distribution here, so it's considered as 0. Sorry, okay, it's 0. Just like the fixed end and also the free end is all 0. That, like I explained that before. Okay, after you get the distribution, then you will get the fixed end moment. So the fixed end moment here is similar with the slope diffraction method. Okay, so you will like first you will get the A, okay, A and B. Then you will have 80 kilonewton here, so you will have this. Okay, so FEM AB, okay, fixed end moment at AB is negative PAB power of 2 over L2. Okay, so you substitute the value into it, you will get negative 45. And FEMBA is positive. Okay, so positive PA power of 2 B over L squared, you will get positive 45. Okay, so this is same with the slope deflection method. Okay, you refer to that. And then FEMBC, okay, BC at these sections. Okay, so you will get negative WL squared over 2 plus WL squared over 12, sorry, over 12. So you substitute the value into it, you will get negative 66.86. And then FEMCB is positive of WL squared over 12, so you get 66.86. And then now you make a table. So step number 4 is you put in the table. So now you have member A, B, C. At C you have component AB, A to B, B to A at point B, and BC. At C you only have CB. Then you substitute the CF into it. So CF is 0.5, 0.5, 0.5 and 0. And the DF will be 1, 0.28, 0.72 and 0. Okay, so FEM you calculate from just now the step 3, you will get negative, you get a value of negative 45 at A, 45 at B, negative 66.86 at B, and then CB is 66.86. Okay. Okay, so now let's start to calculate. Okay, this one is a little bit tricky and might be a little bit confusing at the beginning when you calculate, but you will be okay after that. Okay, so now we go to the A. You can see that negative 45. So here is the fixed end moment. Just now you calculate, and then you will put a DIST, means for the distribution. Distribute. Okay, so negative 45. So in order to balance it to become 0. So negative 45, you will have a positive value of 45. Okay, so negative 45 minus 0. Okay, you will get negative 45. To balance it, you will have a positive 45. So here is 45 and negative 66.86. So 45 minus 66.86, you will get negative 21.86. So to balance it, okay, you will get you will need to, in order to balance it to become 0, okay, so you need to have a positive 21.86. So and then it is distribute 0.28 and distribute 0.72. So 21.86 times 0.28, you will get 6.12. And 21.86 times 0.72, you will get 15.74. Okay, so you settle this now. 66.86. Okay, so here the distribution factor is 0. Okay, so 66.86, in order to balance it, it will be 66.86 times 0. Okay, so it will be 0. Okay, means that it is not distributed to anywhere, and then it is tagged by itself here. Okay, so here is 0. So just now, so the first one I forgot to mention, that here 1 means, okay, the distribution factor. Okay, 41 here. Okay, 45. Okay, to balance it is 45 positive, and then times 1, so it's 1. So now, okay, CO, okay, then we need to bring it carry over. CO is carry over. Okay, CO is carry over. Okay, by using the CF factor. So now we will bring it like BA, you will bring it to AB. AB, you will bring it to here. You will have a cross. Okay, so let me erase this. You will have a clearer photo. Okay, so you can see that, okay, 45 times 0.5. Okay, then you bring it to here, so become 22.5, and then 6.2, and then the distribution at the carryover factor is 0.5, then times 0.5, you will get 3.06. So here the point B, okay, BC is going to bring to CB. 15.74 times 0.5, you will get 7.84, and then 0 times 0, you will get 0. Okay, you bring it to here. So after that, you repeat the same step, same as this. Okay, so 3.06 and 22.5. 3.06, oh, sorry, here is belongs to here. 3.06, you need to balance it, you need negative 3.06 to become 0. So negative 3.06 times 1, okay, the distribution factor, you will get negative 3.06. And 22.5 minus 0, you will have you need to have negative 22.5 to balance it. So negative 22.5 times 0.28 is negative 6.3, and negative 22 times 0.72 is negative 16.2. Okay, and then 7 need another negative 7.87, but then it times 0, so it will get 0. Okay, and then you will have to do it until its distribution become 0, almost 0. Then you will have to do this, repeat 5 times. Okay, normally you need to have 5 times until the moment everything the distribution at almost 0. So I explain this again. Okay, so you can see that after you've done the distribution, then you will have to carry over again. So here we'll bring it to this, and here we'll bring it to here by times the carryover factor. So negative 3.06 times 0.5, you will get negative 1.56, and then this is 6.3 times negative 6.3 times 0.5, you will get negative 3.15. So this one is 0 times 0, you will get 0. Negative 16.2 times 0.5, you will get 8.1. Okay, and then you repeat the same step. Negative 3.15, you need positive 3.15. So positive 3.15, okay, you times 1, you will get 3.15. And then this one is negative 1.53. Then you need another 1.53. Okay, so negative so 1.53 you times 0.28, you get 0.43, and times 0.72 you get 1.1. Okay, and then this one is 8.1 times 0, so you get this. So again the same thing, you get this value, you need to carry over, okay, by using the carryover factor, and then you repeat until you get almost everything at 0. Okay, normally at least 5 times for this moment distribution method. So after you calculate this almost everything at 0, and then you total up the value from here. Okay, so let me clean this. Okay. So let me clean this. Okay, so when you total up the values, okay, negative 4.5 plus 45 plus 3.06 minus 3.06, negative 3.15 plus 3.15, 0.22 minus 0.22, negative 0.22 plus 0.22 plus 0 and 0, then you will get a moment at 0. So at here the moment will be 0. Okay, and then at point PA here, okay, so it's 45 plus 6.12, okay, plus 22.5 minus 6.3 minus 1.53 plus 0.43 plus 1.58 minus 0.44 minus 0.11, and then plus 0.03 plus 0.11 minus 0.03, you will get 67.73, and BC you will get also negative 67.36, and then at point CB you will get 66.65. either you total up everything. Okay, this one you total up, you will get this value. So what you have to do it now is you need to check your answer is correct or not. So for what you did from step 1 until this step 4. So for checking, okay, you can see that at support A is pin support. So at pin support actually there is no moment. So when you get 0, mean it is correct. Okay, and then at support B, okay, so left and the right will be the same. Okay, left and right must be the same because must be 0. So it's clockwise and counterclockwise value must be the same. So it's now you get both same 67.73, one positive, one negative, so it's correct. And then at fixed end support, okay, so at fixed end support, you get positive 66.65. So you get this value. Okay, so after you get this value, what you can do is we need to move to next step to get the support reaction. Okay, so now we are moving to calculate the support reaction. So support reaction is similar to the slope deflection method. Okay, so at span now we need to find the support reaction according to span, span by span, span by span. Okay, so at span AB, okay, so you need to have RA, RB, reaction RB1, we put it here because RB, we have RB1 and RB2, so there's a 80 kilonewton here with a clockwise 67.73 moment. Okay, so you're using the equilibrium equation, total MB equal to 0, so you will get RA equal to 25.03 kilonewton, and total Fy equal to 0, you get RB equal to 54.97 kilonewton. So at span BC, you calculate, you will get RC equal to 114.42, and RB you will get RB2 you will get 114.83 kilonewton. Okay, this one you can practice yourself and check the answer. And then after you get the RA, RB is the total RA, RB1 plus RB2, RB1 plus RB2. So you get this. Okay, and then you need to put in the moment also. Okay, and then the moments from what you obtained from the table, and then the RC. So now you get everything ready. You can plot the shear force diagram and also bending moment diagram. So okay, I show in this example. So RA you have 25.03 kilonewton. Here you have nothing, so it's straight line. And then you have 80 kilonewton moving downward. So we're going upward, we assume positive. Going downward, assume negative. So you have negative 54.97 kilonewton. So here is positive, here is negative. Here you have nothing, so it's a straight line. So at here you face the RB, which is 169.8 kilonewton. So you plot, you're going up here, and then it's 114.83. Okay, and then here you see you have uniform distributed load. So after you deduct, after you calculate, okay, then you will get negative 114.42. Okay, and then you have a RC 114.42, so it's balanced at 0. Okay, so means that this is balanced, and then you need to get this distance in order for you to calculate this area for your bending moment. So how you calculate this area? If you forgot already, then you will use this method. Okay, 114 over 83, 114.83 over 3.5, the total length minus x, okay, equal to 114.42 over x. Okay, 114.83 over this is 3.5 minus x, so this is x. Okay, so after you calculate this, you will get x equal to 1.75 meter. So this is from the mechanics of material, so I won't repeat much lah here. Okay, so you already calculate this, already complete this. Now you need to draw the bending moment diagram. Don't forget you have a bending moment here. Okay, in the shear force diagram is not considered the bending moment diagram here. Okay, because this is force diagram, not the bending diagram. Okay, so you calculate this area, you will get 56.32, and then you minus this one is positive, negative, according to this one. Okay, unit, don't forget. Once if you submit your test or anything, you don't have the unit, then I will deduct your mark. So after that, you deduct this 54.97 minus times 2.25, you will get this value. Okay, so from this you will minus this, and then have you noticed, you can see that the moment here is 67.36. So it must be the same with the moment at the RB here. It's same value. Okay, so here 67.36, and then you calculate, you minus this area, you will get 33.12. Okay, it is curved because this is triangular. Okay, so after that you will plus this, you will add this area, then you will get 67.00. Okay, so minus, so here you can see that this is the load, is the moment here is 66.65, is similar to 67. It's a little bit different than 67 because we have the decimal points. Okay, we use 2 decimal point and 1 decimal point, so it will cause a little bit difference. Okay, so you will get it is balanced. Okay, so this is the step on how you determine the reaction force, the bending moment, and shear force diagram. Okay, for the indeterminate beam. Okay, so here you have another example for you to refer to. You can see that you have A to B, then you have 3-point loads and 1 uniform distributed load, and then you have a free ends here. Okay, so you can calculate the distribution factor, okay, for each. So you can refer it yourself and then check your answer, is it same with it. So you can calculate the K, the total K, okay, and then the distribution factor. Then you will calculate the M moment for each. Okay, then you will get this table, so you can try it at your home, okay, to check with the answer, is it correct or not. And then you will get the support reactions, as I repeated the same thing. Okay, then you will get these support reactions. So after completed, you will get the shear force and bending moment diagram. Okay, so what basically steps are, you have to get the CF, DF, okay, and then you calculate the FEM, and then you make the table to get the moment, and then you calculate the reactions, and then you plot the shear force and bending moment diagram. Okay, so this is the step on how you do it. It is the same thing, keep repeat. Okay, so you need to remember these steps. Okay, so after the method of moment distribution method, so now we have moment distribution, modified moment stiffness moment distribution method. Okay, this is modified stiffness method. So the purpose are the same, the purpose is the same, and then the principle are the same, but now a little bit different at CF and DF. Okay, so this is to simplify the table method, okay, to make it faster to solve. So carryover factor, okay, is either 0 or 0.5 only, but then, okay, fixed. Okay, here you can see that here, okay, if carryover factor CFAB is 0, okay, fixed to pin, and then roller to fix is 0.5, okay, these are the same, and then pin roller to pin roller is 0.5, okay, in between the support, okay, is 0.5. But then you can see that, okay, this is fixed pin, just now is the same, is also 0. Okay, CD is 0. But then here you see, okay, to here roller pin and support to roller pin is 0.5, from here to here is 0.5. But then from the roller pin to roller pin and support, okay, for end support, mean if it's the end is pin or fixed, is pin or roller, so you can see that CFPA now is 0 and CFBC now is 0. It's no longer 0.5. Okay, CFBC, okay, CFCB is 0.5, okay, and then CFCD is 0. Okay, it's free, and so CF is 0. Okay, so the difference here is the support that to the pin or roller end at the end. So this is the difference here. Okay, pin in the middle, okay, pin in the middle is 0.5, 0.5, but then if you pin to the pin roller end is 0. So this is the thing you need to be careful, okay, at the CF. You might be confused with the previous one. Okay, I personally like this modified distribution method better because it is faster. Okay, but you need to be careful with the CF lah. Okay, so this one please digest. Okay, so now we will go to the distribution factor. Distribution factor is also a little bit at the pin end. Okay, so find the value of K. So you can see that now here, find the value of K. Okay, so the F fixed pin is for this one. Okay, K is 0 if fixed to pin. K is equal to 0. And if it is pin to roller, okay, then pin to roller, it will be K equal to 4 EI over L. And if roller to pin, it will be 4 EI over L. Okay, but then, okay, you can see that here, we will go to first example first. A to B, okay, fixed to pin, okay, the distribution factor, okay, for the K, it will be 0. KAB. Okay, this is the value for K. So this is K. Okay, to get the K. Okay, so A to B, fixed to pin, it will be 0. B to A, it will be 4 EI over L, same as the previous method. BC, it will be 4 EI over L. Okay, CB, it will also be 4 EI over L. CD, it is 0. As CD, it is 4 EI over L. Okay, and then DC here is also 0. Okay, and support at, remember for the distribution factor, fixed end to pin or to roller, it will be 0. Okay, and then for this one, pin roller support, pin roller and support. So now here you can see that A is pin, okay, pin n at pin n, it will be 3 EI over L. It is no longer 4 EI over L. Okay, roller pin to pin n support. Okay, pin to pin at n, then it will be 3 EI over L. So look at this. So distribution factor, K for AB is 3 EI over L, pin n to roller. PA is also 3 EI over L because the n is pin. So for modified distribution method, as long as it is n support is pin or roller, then it must be 3 EI over L. Okay, and then pin to fix, it will be 4 EI over L. And then fix n, okay, fix n, it will be 0. So this is the K value for this. Okay, after you get this, then the distribution factor is K over total K. So you will have to use all this K. Okay. So let's go to the example. So example 1. So find the reactions, shear force and moment value for each support member. So support A, B, C. 20 kilonewton, 20 kilonewton, 12.5 meter, 12.5 meter, 15 and 10. Okay. So first you need to find CF. CF AB is 0. Okay, fixed n. CF BA is 0.5, roller to fix. CFBC is 0.5, roller to fix. CFCB is 0 because it is fixed to pin. Okay, and then find TF. KAB is 0, okay, because it's fixed. And then KBA is roller to fix n. Okay, this is fixed n just now. Roller to fix n. Okay, so you will have 4 EI over L. KFBC is also 4 EI over L because it is roller to fixed n. And then KCB is 0 because it started from fixed n to the roller. So this is the 4K. So after you get the K, you get the distribution vector by K equal DF is equal to K over total K. Okay, so TAB is 0 because KAB is 0. 0 over 0 AB, so it's 0. Okay, distribution you can straight away not write 0 because fixed n is 0. Okay, and then DFBA is equal to KBA over KBA plus KBC, so you get 0.5. Okay, after you put in the value, and then DFBC is also 0.5. Okay, so you can check with just now DFBA is 0.5. So 0.5 plus 0.5 equal to 1. Okay, so it's okay. So DFCB is also 0, it's fixed n. Okay, so after you get all this, then you will calculate the fixed n moment. Same method as just now. So you have a point load, then you use this negative PAB power of 2L. Okay, then you will get the moment value, fixed n moment for AB and BA. Okay, and then for BC sections, you also use this formula. Okay, but now it's not at the middle. The load is at 15 from the left, 10 from the right. Okay, the value is here. So you will get negative 48 and negative 72 for both. This is negative 48. Okay, and then this is BC. FNCB, this is positive. Positive 72 kilonewton meter. Okay, normally at here, you remember here is counterclockwise, here is clockwise. So at left side will be negative, at right side will be positive. After that, you put into the table. So you have table, okay, similar table, but then this distribution not need to have 5 times, no need. Okay, it is faster to get 0. So remember you have A, B and C. Okay, and then the CF you put in AB is 0, BA is 0.5, BC is 0.5 and CB is 0. So the distribution factor you put in also AB is 0, BA is 0.5, 0.5, 0. Okay, so you put in the FEM value for this. Okay, then you will start to do the distribution. Okay, negative 65, you need another 65. So here have no negative. Okay, 62.5 times 0. Okay, the DF factor. So the distribution factor, this one. So you get 0. So 62.5 minus 48. Then you will get 14.5. So you need negative 14.5 to balance it. So distribute to both PA and BC 0.5, 0.5, you will get negative 7.25 and negative 7.25. This 72, you need another negative 7.72 to balance it, but then this is 0 because the distribution factor is 0. So negative 72 times 0, you get 0. What is the first thing is, here if the distribution is 0 and 0, straight away you can write 0. You no need to count, okay? If you already used to the method, you can straight away put 0. And then this one, we will have to bring it to the right. This one, you bring it to the left by calculate the CF factor. Okay, so 0 automatically you put in 0. This one 0, you automatically put in 0. No need to think. Okay, so negative 7.25 times 0.5, you will get negative 325. Okay, so this one negative 7.25 times 0.5, you will get negative 3.625. Okay, so this CO, what you have to do is you need to put the distribution factor again. So distribution factor is 0, so times 0 you will get 0. Okay, so for this C also, the distribution is 0, so you can straight away put 0. Okay, so here is 0, here is also 0. When you put things also, here is 0 and 0. So done. You can see that the step is become shorter. And then the end moment, you will total up from here to here. Then you will get 66.125. Then this one you get 55.25. This one you get negative 55.25. And then this is 6x.375. So for checking, you can see that, okay, at fixed support, you will have moment, which is correct. At point B, left and right, okay, the moment must be 0. When you total up, this must be 0. Okay. So this is 55.25 and negative 55.25, so it's correct. And this is another fixed end, so also have moment, so it's okay. So when you plot, you will get this. So what can you do is, now you can get this support reaction. So support reaction, you substitute, you calculate from span AB, span BC. Okay, then you will get RP1, and then you will get RA, you will get another RP, you get another RC. So after you obtain this, you will put into this. Okay, and then again, you draw the shear force and bending moment diagram. Okay, so the steps are the same for the both methods. Okay, but the modified stiffness method, it will be different at the pin end support and roller support at the end, at fixed and at end. Okay, so you need to be careful with it, and then you can proceed to practice more. Okay, so this is another example where now you have a free end at point D. Okay, and then you can see that you have a support A fixed. Okay, support B is roller, support C is roller. So okay, first you find the CF. Okay, CFAB is 0, which is the fixed end. CFBA is 0.5. CFBC, okay, BCC is the end support, which is roller, so it's 0. Okay, so CFCB, C to B is 0.5 because it's is pin end to the pin end to the roller, so it's 0.5. And then CFCD is 0 because it is to the free end, and DC is also 0 because it is free end. Okay, 0 and 0. Okay, so after you get the CD, then you will get the DF. So the DF, you need to get the K value before you get the DF. So KAB is 0 because it's free end, fixed end. KBA is 4EI over L because it's roller to fixed end. KBC is now 3EI over L because it is roller to roller end. And KCB is also 3EI over L because this is from the roller end to the pin. It's roller end to the roller. Okay, and then KCD now is 0. KCD now is 0. Okay, so after you get this, you will get the value of distribution factor. AB you will get 0, and then BA you will get 0.67, and then you will get, if you want to have faster way, and then you can, using the FBC is 1 minus 0.67, you get 0.23, because the total must be in 1 at 1 support. Okay, if you use the equations, if you use this equation, okay, for the KBC over KBA plus KBC, you will get 0.33 also. Okay, then you will get the KCB, you get a value of 1. Okay, and then the KDC is 0 at the free end. Okay, so after you calculate that, after you've done that, and then now you need to get the fixed end moment. Okay, fixed end moment by using the equation of this. Okay, you will get this value. So you can also check by yourself, do the practice to get the answer that's same with mine. Okay, and then also the FEMCD. Okay, FEMCD here, C to D here is 20 times 10, because it's just direct, you get the moments of it. Okay, okay, and then FEMDC is 0, because there's point here, at here there's no force, so here is 0 kilonewton meter. Okay, so you build the table. Okay, you have point A, B, C, D. You insert the value of this. Okay, you will get 0, 0.5, 0, and then 0.5, 0, 0. Okay, and then you will have the DC. You put in the value, you get this. Then you put in the moment. You repeat the same step. Okay, 40 times 0, you get 0. You can straight away write 0. And then this one is 40 minus the 133.36, you will get negative 93.33. So you need positive 93.33 times 0.67, you get this value. And then times 0.33, you get this value. So this one is the same. Okay, you will get the value. So this is directly moment distribution is 1. So you directly put here, and then here is 0, 0. So, and then carry over. Okay, from here you carry to here and here. So 0, you can straight away put 0. And then 62.53 times 0.67, you will get this. Okay, okay, sorry, times 0.5. Okay, confused a bit. 0.5, then you get this. Okay, then this one you carry over. Okay, times 0, times 0. Okay, here is the carryover factor, you will get 0. And then 133.35 times 0.5, you will get 66.67. And then this one above is 0, so you straight over here is carry over also 0, 0. Okay, so here repeat the same thing. Okay, this one times the distribution factor, you get 0. This one 66.67, distribute 0.67, 0.633, you get this. And this one is 0, 0, also 0. Here is 0. So you solve another round again. Okay, solve another round, you get this value, and all others are already 0. And then this one you times 0, the distribution factor. Okay, you get 0, 0, 0, 0, 0. You see, you only need to distribute 2 times. Okay, distribute 2 times instead of 5 times the original method. So you get the fixed end moment, negative 31.07. Okay, at the fixed end. So correct, fixed end you have a moment. At point B you have you must have total 0. So correct. At point C also total is 0. Correct. And then free end no moment, so it is correct. So after this step, again the same step, you will now you have to, after that also you will get the shear force and bending moment diagram and reaction, support reaction, shear force bending moment diagram, and then you can go on. So now another example I will show you up to the table step also. Okay, this is same method as just now the first method. Okay, but the difference now is the CF and the DF factor is already changed. Okay, this one is same with the example for the original moment distribution method, so you can compare. Okay, so now A to B, okay, A to B is 0.5, but then B to C is now already become 0. Okay, B to C is 0.5, and then C is fixed, and so it is 0. Okay, so now you can see here. Okay, 0.50, 0.50. And then the KAB now is 3EI over L. KBA is 3EI over L because it's pin N. Okay, KBC is 4EI over L. Okay, KCB is 0 because it's a fixed N. Okay, so DFAB you will get 1. Okay, at the pin roller is normally 1. You can memorize actually. Okay, pin roller it will be 1, and then at the fixed end you will get 0. So this one actually you can straight away put 1 and 0 if you already are used to it. Okay, and then KBA you will use the value of this 3EI over L over 3EI over L plus this one after you calculate it, and then you will get 0.67. Okay, and then the KPC is 1 minus 0. Sorry, not 0.67, 0.23. Okay, 0.23, and then this one is 0.77. So after you calculate it, you can calculate the fixed end moment. Okay, fixed end moments are the same, no difference. Okay, you put into this table. Okay, after that you repeat the same step for the distribution carryover factor, and then you will get this value. Okay, at the pin end is 0, and then at support must be the same with total equal to 0, and then you get a fixed end with a moment. Okay, then now I will explain about the sway and unsway stiff frame. Okay, it is basically the same concept on how to do it. Okay, if the structure is stable in any condition, then it will call non-sway or either unsway structure. Okay, so for this sway frame, okay, frames that are non-symmetrically or subjected to non-symmetrical loadings and have tendency to sway. Okay, so when load applied, it might sway. Okay, when you're being just roller supported, you can see that you have a sway. You will sway. You will like move. Okay, when the load applied towards the right, this frame will tends to move, and then it will cause a deflection. Okay, so this is a sway frame. Okay, so example here, draw shear force and bending moment diagram to rigid frame as this structure below. So you can see that, and this is the frame that you have fixed support at A, and then the pin support at D, and then the pin support at C. So you have load, okay, on the top of AB and BC. Okay, so here is EI, but here is 4 over 3 EI at BC. Okay, so you can see that the distribution factor, okay, AB is 0 at the fixed end, and then CB and DB is 1 because this is the pin support. Okay, and then you can see that at joint B, when we are on the beam method, it is only 2 members, but now we have the 3 members because at B it will connect to A, connect to B, and connect to C, and connect to D. So the total K is now 4 EI. Okay, when after you total up here, you calculate the K. The K you can use the same method lah. Okay, you calculate the K, you will get the total K, and then is 4 EI. And then the distribution factor, okay, after you calculate it, you will get 0.25, 0.5, and 0.25. This one you can practice lah. Okay, so now I explain the method on how to do it. So again, the same thing, you will calculate the fixed end moment, just like how you do on the regular beam. Then you will put in, okay, A, B, C, and then now you have A to B, B, A, and then B, C, and then BC will distribute to CB lah. BD will distribute to DB when you do the distribution, the carry over. Okay, so you can also try yourself with this table. Okay, and then you will get the fixed end moment value like this. So after you get that fixed end moment, also the same thing, you will need to get the reaction force for each support. Okay, AB, BC, and also BD. So after you get all of it, then you will draw the moment distribution factor. Okay, for the support AB, and then support BD, and then support BC. Then you will get this. Okay, so thank you for watching this video. I hope you guys will practice this and then try to learn it. If anything, you can telegram me or PM me personally for any questions. So thank you for watching.